presenting for the group from University of Maryland, on the work for novel neural filter to improve accuracy of neural network model for dynamic system.
So hello everyone. I'm Parham Oveissi. I'm a PhD student in the Mechanical Engineering Department at the University of Maryland, Baltimore County. Today I'll be presenting our research on neural filter to improve accuracy of neural network models of dynamic systems. I would like to acknowledge Turibius Rozario, the undergraduate student who actually worked on this project, and we conducted this research under the supervision of Dr. Ankit Goel at the UMBC. So neural networks are pretty powerful for modeling dynamic systems as they can learn nonlinear behaviors directly from data. And that's why they are used in many different fields in science and engineering, such as UV trajectory prediction, weather forecasting, and even medical diagnostics. But the problem is their long-term predictions tend to drift as the small errors accumulate over time, and the results might actually diverge from reality. To tackle this, we propose the neural filter, which is inspired by the standard Kalman filter. And the idea is pretty simple. So you use the neural network to do the state prediction for nonlinear systems, and then you feed back a measurement in order to correct those small errors that are accumulating over time. And with this approach, we've seen big improvements across multiple nonlinear systems. And I would say the main contribution would be the fact that you can actually use pretty simple neural networks instead of those well-trained neural networks with large data sets. And you can just use a measurement feedback in order to reach the accuracy of those well-trained models. So let's consider general discrete time nonlinear dynamical system described by the function f, where the next state of the system actually depends on the current state and the current input to the system plus a process noise, which is basically representing the uncertainty in the system. And as for the measurements, we do have a measurement model. We're observing some measurements from the system. And then our goal is to predict the state of the system using the neural networks and then using the available measurements in order to correct those state estimates. And for simplicity in this work, we're assuming that we know the measurement model, so the function g is actually known to us. And we are trying to approximate the function f and then correct the predictions using measurements, using real-time measurements. Let's consider a general dynamic system. The lambda operator could be either a time derivative or the forward shift operator, depending on whether we're dealing with a continuous time system or a discrete time system. And then the idea is to approximate that function f using a neural network. And but to train a neural network, we require a data set. And in order to generate data, we are simulating the nonlinear systems one step forward in the future from randomly selected initial conditions. And that's how we get the training pairs x naught, u naught, which are the initial state and the control input, and the output xts, where ts is actually our discrete sampling time. And we use the MATLAB deep learning toolbox, or to be more specific, we use the DL network architecture to train the models with atom optimizer in mini-batch mode to get the neural network model. And then we reserve some part of data for validation. But the challenge here is that if we only rely on the open loop predictions of the neural network, as I mentioned earlier, no matter how great your neural network is, or how many data you used in training your data set, in your training the model, you still, even though you might have like small errors, these small errors will accumulate over time, and then your estimations will basically diverge. So that's where the neural filter comes in. It's inspired by the extended Kalman filter. The idea is straightforward. Instead of just trusting the neural network, we combine its predictions with the available measurements. And so the neural network gives us the state of the system, the prior estimate of the state of the system, and also we do the prior state estimation covariance, and then we use the measurement coming from the system to correct this state estimate to get the posterior state estimation and the covariance matrix. In order to compute these posterior estimates, we do require the state transition matrix and the measurement matrix, and we get that from the Jacobian of the neural network. And the benefit of that would be like we are incorporating the measurement in the neural network predictions to basically compensate for those small errors. So and this is how we do the we compute the Jacobian for the neural network. And the way we do it, so the neural network is basically it's a composition of multiple layers, and each layer takes an input and applies some weights and nonlinearities, and then passes it to the next layer. So if we denote the input to the first layer, to the ith layer with like xi, and then the output would simply be xi plus 1 ni xi theta I, where theta I are those the neural network gains, the neural layers gain. So basically each layer's gains, and those ni's are basically those individual layers of the neural network. And to compute the Jacobian, so if we use this formulation, we can finally rewrite the final network output as a weighted sum at the last layer. And to compute the Jacobian, we can use the chain rule. That means we simply just take derivatives layer by layer, starting from the last layer to the first layer. And this Jacobian basically tells us like how the neural network model is propagating like locally and evolving locally. So this Jacobian is basically the product of the layer derivatives multiplied by the weights of the last layer. And that's how we actually get the state transition matrix AK from the neural network. To demonstrate the effectiveness of this approach, we are considering multiple nonlinear systems. We start with a pretty simple classical nonlinear system, the simple pendulum. The equations of motion are given in the first equation, and then we write it in the state space form. And as for the measurement, we assume that we can measure the angle theta. And in order to generate training data, we simulate the nonlinear model for 30,000 samples from random initial conditions in that specific range using MATLAB ODE solver. And then we reserve some of the data for training and some for the validation. For this example, we're actually considering two different neural network structures. One is actually a larger neural network, the other one is a much simpler one. And the idea is that we want to show that you don't necessarily need like a large neural network. Even though like if you only use the neural network, you might get like worse results. But when you add a filter, it doesn't really matter whether you're dealing with a lot of data or like a complex neural network model or a simpler one. They can reach relatively like the same prediction accuracy. So for the validation setup, we use a randomly selected initial condition. For example, for the plot, you see that's the initial condition that we've selected. And the neural network is actually initialized with the true state, so we want to make the work pretty easy for the neural network. So we basically start from the actual true state. But when it comes to the neural filter, we initialize it with no prior knowledge. That means we start from 0. And then the key observations from the plots, as you can see that the predictions of the neural networks, as the time goes on, they tend to drift. But the predictions that are computed by the neural filter, since they're using the measurement feedback, they tend to remain bounded and accurate. And in the second plot, you can see this is with the second architecture, which is a much simpler neural network. It's pretty simple. It's just one hidden layer, 2 neurons. You can see like when you only use the neural network itself, it's giving us like worse results. And but then with the neural filter added, you basically get to the same level of performance. And in these plots, you can see the two states of the system, the evolution of the two states, and also the errors and the trace of the state estimation covariance, which kind of approximates the score of the second norm of the posterior estimation error. We do the same thing for basically another nonlinear system. The Van der Pol oscillator equations are given in the first equation, and then we write it again in this state space form. Assuming that we can somehow measure the first state, we're just trying that with this new Van der Pol oscillator, with this new system. Again, we are initializing, regenerating the data by simulating a model starting from random initial conditions. And you can see the results for the Van der Pol oscillator with the neural network only and the neural filter added. And for this example, we're using 2 hidden layers for the neural network with 10 neurons, ReLU activation functions, and a linear output layer. And again, we're training using Atom Optimizer with 32 bat size. And as you can see, again, the pure neural network predictions, they tend to drift, but adding the neural filter will basically compensate for those small errors that are coming from the neural network predictions. And again, in this case, we initialize the neural network's prediction from the actual true state, but they still tend to diverge. But we start the neural filter from no prior knowledge, so basically we started from 0. And you can see the results in this plot. And we try with a nonlinear chaotic system, the Lorenz system, with the 3 states, and you can see again we're assuming that we can measure the first state, the same architecture, and these are the results for the Lorenz system. For this case, we're using 3 hidden layers with 10 neurons, ReLU activation function, and again a linear output for a linear output layer. And I'm then again optimizing using Atom Optimizer. For this setup, that's the initial condition that was randomly chosen, and the neural layers are initialized with the true state again, and a neural filter starts at 0 like the previous example. And finally, the last example would be the double inverted pendulum, and where we are measuring both the 2 angles of the system, theta 1 and theta 2, and for this one we're using 200,000 samples, which are generated again by simulating a system from random initial conditions. And these are the equations of motion of the system. And finally, you can see the results for the double inverted pendulum. This one uses 4 hidden layers with 10 neurons, ReLU activation function, a linear output layer, and again using Atom Optimizer, we're training the neural network, and then you can compare the results from the predictions that are coming from the neural network, and which are corrected by the neural filter on the second column. So in this work, to wrap up, we introduced a very basic, simple idea using a neural filter, which improves the state prediction accuracy for neural network-based models of dynamic systems. And it is inspired by the extended Kalman filter, and with the explicit Jacobian computation of the neural network. And we evaluated on 4 nonlinear systems to see the effectiveness of the approach. And then the key outcomes would be neural filters predictions remain close to the true states, but on the other hand, the pure neural network predictions may diverge over time. And then we demonstrated the paper demonstrates the enhanced accuracy, robustness, and reliability for neural network-based state estimation in nonlinear dynamic systems. I'd be more than happy to take any questions.
So, any question from the audience? Well, so this is not really my expertise. So my question is that there are also some concept about like adaptive attended Kalman filter where you change the feedback. I mean the magic key of the Kalman filter, right? So why we need the neural network to add some complexity in the system?
Okay, so to be honest, this project was so we were working with this undergraduate student who was doing a lot of neural network stuff, and then we do control and estimation, and he was like, why don't we like use neural networks to predict the state of the systems? And so this work is mostly maybe intended towards the machine learning community, because they use the neural networks for predicting the states of the system, and we're like, we use Kalman filter all the time. Why not just using measurements to correct these predictions that are coming from the neural networks?
Yeah.
So that's how we actually ended up doing this work, and yeah, I guess that would be my answer to it.
Because I have the question about the panel, when control engineer is spear and replaced by computer scientist. That's why I asked.
Right.
Hi, sorry, I came slightly late, so I missed a little bit about the filter. So, are you using the results from the Kalman filter to modify the neural network itself, or is it something you just add to the output of the neural network at runtime?
So you basically use the neural network. So this is like two-step process. You use the neural network to get the prior estimate instead of just using so let's say we don't have the model. So in this case, all the data are coming from simulations, but you might be actually dealing with an actual system. So you might get the data, and you can use that in order to train a neural network model based on the data, and then use that neural network model to predict the state at the next step. And then that would be the prior estimate, and then we use a measurement that is coming from the actual system in order to correct those predictions.
So it's at runtime, okay.
Yes.
So the neural network itself does not change
No.
after that, like once it's done, even as you get new measurements.
Yes, exactly. We use it for offline predictions.
Is it possible to incorporate the idea that you just said? Like
Continue training the network.
Yeah, you use the Kalman filter as the system to train it.
You can do that, but I would say like the main contribution here would be basically you don't want to like over complexify the neural network stuff. So use the simple ones, and then do the predictions. The Kalman filter will just fix it for you. You probably can do that too. You can incorporate the Kalman filter in the neural network training to get better training. But we were like, you don't need to do better training. Just do like maybe you have access to limited data. Maybe you don't have access to like huge computational resources. So you can just do a simple modeling and then use the measurements to correct those predictions.
But then you were saying that even the model is incorrect, you can use Kalman filter to fix it. I'm not sure.
No. So I'm saying that no matter how your model is, your neural network modeling is good, so you will still have prediction errors. Because like, let's say you have an amazing model, it makes an error like in the first prediction, and then over time when you use that, so because you feed that prediction to the neural network model to get the next prediction, right? So and these errors will accumulate over time. It doesn't matter how good your model is. So even if you use like a very complex neural network model with a lot of data, you still will have a bunch of errors like over the time, and then that's how you can fix it.
So thank you very much for your contribution.